You ever have that feeling? Like you totally aced all the practice runs, you knew it inside out, but then the actual game starts and bam, curveball.
Oh, definitely. Like a team just crushing it in scrimmages and then freezing up in the actual championship.
Exactly. Or, that recipe you've perfected and suddenly it just flops.
Yeah.
That weird gap, that promise versus the sometimes harsh reality.
Mm-hmm.
That's actually a perfect way to think about what we're diving into today in machine learning. There's this sneaky issue called overfitting.
Right. It's that frustrating moment when your brilliant AI model, the one scoring like 100% on all the data you trained it on,
Yeah.
suddenly seems completely lost when it sees something brand new. It's like that student who just memorized answers for one specific test paper.
Ah, okay. They know those answers perfectly, but ask them something slightly different.
And they're clueless, no real understanding, just memorization.
Gotcha. So for this deep dive, our mission really is to tackle this overfitting villain. We want to help you understand what it is, how you spot it.
And crucially, the ways we can actually fight back against it, the sort of heroic techniques.
Think of this as your shortcut, your express lane, to getting a grip on a really fundamental challenge in AI.
And we're drawing on some really interesting stuff today. We've looked into materials about how we evaluate machine learning models properly,
Yep.
and also some resources that dive into actually building neural networks from the ground up. So the nuts and bolts.
Cool. So we get both the high-level view and the details.
Exactly. It helps understand the whole picture, not just the what, but the why and the what next.
All right. So here's the plan. First up, we'll really paint a picture of this promise versus failure thing using some examples from the world of data.
Right. Then we'll build a little suspense.
Yeah.
Define what overfitting really is. Get technical, but keep it clear.
Then, detective time. We investigate the signs, the clues that overfitting is happening.
We'll even dig into why it happens. What's the root cause?
And then, the big finish. The resolution, the tools and techniques we use to, win against overfitting. We've even got a buzzword breakdown and an optimization corner plan.
Sounds like a plan. Let's jump in.
Okay, let's start with setting the stage. Promise versus failure. Give us an example.
Okay, imagine you're trying to predict, say, house prices based just on square footage. Pretty standard.
Right.
But maybe the real relationship isn't just a straight line. Maybe really big houses jump disproportionately in price, or there's a sweet spot. If you just try to draw a simple straight line through all that data...
You're going to miss, right? It won't capture that curve.
Exactly. That's underfitting. Your model is too simple, too basic. It has high bias, we'd say. It's just not capturing the underlying trend.
Like trying to draw a circle with only straight rulers?
Yeah.
Just doesn't work well. Okay, so that's underfitting. What's the flip side?
The flip side is you take that same data, maybe with a few weird outliers, like a house sold super cheap to a family member, or one went way high because it had, I don't know, a recording studio. And instead of a simple line, you draw this incredibly complex, wiggly line that goes exactly through every single point. It hits the cheap one, it hits the expensive one, it hits everything perfectly.
So on the data you have, it looks amazing, like zero error.
Suspiciously amazing. That's overfitting. It's learned not just the general trend, but also all the random noise in those specific oddball houses.
So visually, the underfit line is clearly missing the pattern, but the overfit line looks too perfect.
Precisely. It's like it memorized the training data, noise and all.
Okay, let's think about classification.
Yeah.
Separating cats and dogs, maybe?
Good example. Say you have photos, and there's a generally clear way to tell them apart based on features like ear shape, snout length, whatever. An underfit model might draw a really simple boundary, maybe just a straight line, that misclassifies a lot of obvious cats and dogs. It's too basic.
Okay.
An overfit model, though, it might draw this incredibly convoluted, intricate boundary that perfectly separates every single training photo, even the blurry ones, the ones with weird lighting.
So it's fitting to the imperfections in those specific photos.
Exactly. It's learning the noise. So when you show it a new photo, maybe slightly blurry in a different way, that super specific boundary might suddenly put it on the wrong side. A cat gets called a dog.
Okay, this is definitely setting up our villain. Overfitting. So formally, it's when the model learns the training data too well.
Yes, including noise, including outliers, to the point where it loses its ability to perform well on new, unseen data. Its generalization suffers.
And we need to contrast that with underfitting too simple and what we actually want.
Which is that balanced fit, the Goldilocks zone. Just complex enough to capture the real signal, but not so complex it starts memorizing the noise.
Right. Now, you mentioned an analogy, the dartboard. That sounds helpful.
Yeah, it's a great way to visualize bias and variance. Think of the bullseye as the true pattern you want your model to predict.
Okay, got my dartboard ready.
All right. High bias, like our underfit model is like consistently throwing your darts way off target, but they're all clustered together in the wrong spot. You're consistently wrong in the same way.
So low accuracy, but the errors are predictable, maybe?
Kind of, yeah. Low variance because the darts are clustered. Now, high variance, this is often linked to overfitting, is like your darts are scattered all over the board.
Whoa, okay.
Some might land near the bullseye, maybe even hit it by chance. It's like getting good performance on your specific training data, but your throws are inconsistent. On the next round, with slightly different conditions, you'll miss wildly.
So the performance is unreliable on new throws, new data.
Exactly. So you can have high bias, low variance, consistently wrong. Low bias, show variance, scattered, sometimes right, sometimes wrong, like overfitting. High bias, shy variance, just scattered and nowhere near the target, a mess.
And the dream.
Low bias, low variance, consistently hitting the bullseye, accurate and reliable.
Okay, so that high variance, that scattering, that's a big clue for overfitting. Let's dig into that more. Bias and variance.
Right. So bias, technically, is the error between your model's average prediction and the correct value you're trying to predict, measured on the training data. High bias means, even on the data it saw, the model is fundamentally wrong. Its assumptions are off.
Like the ruler trying to measure temperature. The tool itself is mismatched.
Good analogy. Now, variance measures how much your model's predictions change if you trained it on a different set of training data. High variance means the model is very sensitive to the specific data points it was trained on.
So if we swapped out the training data for another batch, a high variance model would give totally different predictions.
Potentially very different, yes. It learned the specifics, the noise of the first batch too well. That's why it doesn't generalize, it's unstable.
Okay, high bias. Fundamentally wrong assumptions, high variance. Overly sensitive to specific training examples, unstable predictions on new data. And this brings us to that trade-off you mentioned.
The bias variance trade-off. It's fundamental. Generally, as you make a model more complex, add more features, more layers in a neural network.
You give it more power to learn intricate patterns.
Right. So the bias tends to decrease. It can fit the training data better, get closer to the bullseye on average for that data.
Oh.
But that increased complexity often makes it more sensitive to the specific training data points, including the noise. So the variance tends to increase.
So less bias, but more variance. And if you make it too simple.
Less variance probably, but more bias. It's a balancing act. You want that sweet spot with reasonably low bias and reasonably low variance.
The Goldilocks zone again. Okay, this feels like a good moment for our buzzword breakdown.
Perfect. The key buzzword here is generalization.
Generalization. What is it exactly?
It's simply the model's ability to perform well on new, unseen data it wasn't trained on. That's almost always the ultimate goal, right? We don't just want a model that's good on the data we already have. We want it to make accurate predictions or classifications out in the real world.
So overfitting is basically the enemy of generalization.
It's generalization's kryptonite. An overfit model might look great on paper, on the training stats, but it fails the real test because it didn't learn the general patterns, just the specific noise of its training set.
Okay, got it. Overfitting equals bad generalization. So how do we spot this? If we're building a model, what are the warning signs, the red flags?
The biggest red flag, absolutely, is seeing a big gap between how well your model performs on the training data versus a separate set of data you held back the validation set.
The practice test versus the real test again.
Exactly. If you're getting, say, 99% accuracy on training data, but only 70% on validation data, that's a huge warning sign.
Makes total sense. What else? Any other clues?
Another key sign is watching those performance metrics during training. You'll usually track both training performance and validation performance. If you see the training score continuing to climb, getting better and better.
Which sounds good.
Initially, yes. But if at the same time the validation score starts to flatten out, or worse, starts to decline, that's a classic sign that you've started overfitting. The model is now learning things specific to the training set that are actually hurting its ability to generalize.
Wow. So getting smarter on the training data actually makes it dumber on new data after a certain point.
Precisely. It's optimizing for the wrong thing past that point.
Okay, so big performance gap, validation score dropping. Any other major signs?
Just the sheer complexity of the model relative to your data. If you have like 100 data points, but you're using a neural network with millions of parameters,
Uh-oh.
yeah,
Mm.
that model has so much capacity, it can essentially just memorize those 100 points, noise included. It's not forced to find the simpler underlying pattern because it has enough brain power to just remember everything.
Overkill. Trying to crack a nut with a sledgehammer.
Something like that. It lacks the constraints needed to find the general signal.
Okay, those are definitely clear warning signs. We should probably,
Hmm.
you know, highlight them.
Red flags indeed. So we know what it is, we know how to spot it. Now, the deeper question, why does it happen? Are some approaches just riskier?
Yeah, our sources mentioned algorithm tendencies. Are some machine learning algorithms just more prone to this?
Yes, definitely. Algorithms that have high inherent flexibility, what we often call high variance algorithms, are more susceptible. Think of things like decision trees, especially deep ones.
Okay.
Also, k-nearest neighbors, KNN, particularly with a small k, and support vector machines, SVMs, especially with certain kernels. These models can, in theory, create very complex decision boundaries or fit functions.
So their strength, their flexibility is also their potential weakness.
Exactly. That flexibility allows them to fit the training data very closely, sometimes too closely, capturing noise and leading to poor generalization. You need to be careful tuning them.
And the other side, low variance algorithms.
Those are typically simpler models like linear regression, logistic regression, or linear discriminant analysis, LDA. They make stronger assumptions about the data structure.
Like assuming a linear relationship.
Right. Because they're less flexible, they can't easily twist and turn to fit every little quirk in the training data. So they're less likely to overfit.
But the risk there is.
They might underfit if the true relationship is complex. They might be too simple to capture the real pattern. High bias again.
Okay, so high variance algorithms. Powerful, flexible, but overfitting risk. Low variance algorithms.
Yes.
Safer from overfitting, but risk underfitting. And the fundamental reason the high variance ones overfit is they learn the noise.
That's the heart of it. An overfit model isn't just learning the true signal, the real underlying relationship in the data. It's also modeling the random fluctuations, the errors, the static. It's treating noise as if it were a meaningful pattern.
And noise, by definition, isn't predictable or repeatable in new data.
Exactly. So a model that has learned the noise from the training set is going to make mistakes when it sees new data that has different noise or no noise.
Okay, the villain is unmasked. It's the flexibility combined with learning random noise. So, how do we fight back? Time for the resolution, the victory.
Absolutely. This is where we roll out the toolkit. Welcome to the optimization corner.
All right, bring on the tools. What sort of... I see regularization here, L1, L2. Sounds a bit mathematical.
It is, but the concept is quite intuitive. Regularization basically adds a penalty to the model based on how complex it is specifically, often based on the size of its internal parameters or weights.
So you're discouraging complexity.
Precisely. You're encouraging the model to find simpler solutions, solutions with smaller weights. L1 and L2 do this slightly differently. L1 can even push some weights to exactly 0, which helps with feature selection, but the goal is the same. Penalize complexity to reduce variance and fight overfitting. It's like telling the model, hey, keep it simple.
Okay, make the model less likely to go wild fitting noise by making wildness costly. I like it. What's next? Early stopping.
This one is super practical. Remember how we said the validation performance can start to drop even while training performance improves?
Yeah, that weird divergence.
Yeah. Early stopping just says, monitor the validation performance. And when it stops improving or starts getting worse, just stop training.
Just pull the plug.
Pretty much. You save the model from the point where it had the best validation performance. You prevent it from going further down the overfitting path. It's very effective and widely used.
Simple but smart. Okay, pruning. Sounds like gardening.
It is, mainly for decision trees. After you've grown a potentially complex tree, pruning involves cutting back branches that don't add much predictive value, or maybe only cover a few noisy training examples.
So simplifying the tree after it's grown.
Exactly. You trim off the parts that likely just learn noise, leaving a more robust, generalizable tree.
Cool. Next, dropout. This one sounds interesting. What's dropping out?
This is the technique specifically for neural networks. During each training step, you randomly drop out, temporarily deactivate a fraction of the neurons in the network.
Randomly switch them off.
It forces the network to become more redundant. It can't rely too heavily on any single neuron or pathway because it might get dropped out next time. So other neurons have to learn to compensate. It makes the network more robust and less likely to fit specific noise patterns involving just a few neurons.
Like forcing teamwork by making individuals less reliable. That's clever.
It is, and it works surprisingly well. Okay, what else? Data augmentation.
Augmentation, like making more data.
Sort of. You take your existing training data and create slightly modified versions of it. If you have images, you might rotate them a bit, zoom in or out, change the brightness slightly, add a tiny bit of noise.
Ah, so you're expanding the training set with realistic variations.
Exactly. You're teaching the model that these small variations don't change the fundamental label. It's still a cat, even if slightly rotated. This makes it learn more robust, invariant features and helps it generalize better, especially when you don't have a ton of original data.
Makes sense, given more variety to learn from.
Oh,
Okay, couple more here, mostly for neural nets. Batch normalization and weight decay.
yeah. Batch normalization is a technique applied within the network layers that helps stabilize training and can have a slight regularizing effect too. Weight decay is essentially another name for L2 regularization, very commonly used when training neural networks. It directly penalizes large weights during the update process.
Gotcha. And these last two, mix up and cut mix, they sound pretty advanced.
They are newer, more advanced forms of data augmentation. Mixup creates new training examples by literally mixing two existing examples, like averaging the pixels of two images and also averaging their labels. Cutmix involves cutting a patch from one image and pasting it onto another, adjusting the label accordingly.
Whoa, okay, that sounds abstract, but I guess the idea is to force the model to learn even more general features.
That's the intuition. They push the model away from memorizing specific examples and towards understanding broader concepts.
Wow, okay, that's a serious toolkit against overfitting. Regularization, early stopping, pruning, dropout, data augmentation in various forms.
And they all, in different ways, aim to reduce that high variance we talked about, nudging the model back towards that balanced bias variance sweet spot.
Fantastic. Okay, we've covered a lot, what overfitting is, the signs, the causes, the solutions. So now it's time for a little challenge for everyone listening.
That's right. We've done the deep dive. Now it's your turn to synthesize. Here's the question. In your own words, why is a model that gets 100% perfect accuracy on its training data potentially a bad sign? Why might that model actually perform poorly in the real world?
Think about noise, generalization, that promise versus failure idea. Give it a thought. Okay, while you're pondering, let's connect this back to those sources on building neural networks from scratch. How does overfitting show up there?
Well, when you're building a neural net, you decide the architecture, how many layers, how many neurons per layer. It's really easy to make it too complex for your dataset size.
More capacity than needed.
Exactly. And that excess capacity makes it very easy for the network to just memorize the training data, noise and all. Also, how long you train it, the number of epochs. If you just keep training and training without watching that validation performance.
You'll likely walk right past the optimal point and deep into overfitting territory.
Absolutely. The model just keeps refining its fit to the training data, including the peculiarities.
And what about the actual mechanics, the forward and backward passes our sources mentioned?
During the forward pass, if the network is too complex, it can learn incredibly specific pathways to get the right answer for the training examples. Then, during backpropagation, the backward pass, it adjusts its weights to minimize the training error. If it's aiming for zero training error on noisy data, those weight adjustments will be tailored to fit that noise perfectly.
Which means those weights won't be right for new data without that exact same noise pattern.
Precisely. The learning process itself becomes hyper-specific to the training set.
Okay, that really ties it all together.
Huh.
Great. So let's recap the key takeaways from this deep dive.
Okay. We started with that hook. Perfect training performance doesn't mean real-world success because of overfitting. We defined overfitting as learning the training data, especially the noise, so well that the model fails to generalize to new unseen data.
We contrasted it with underfitting, too simple, high bias, and talked about the dartboard analogy for bias and variance. Overfitting often means high variance.
Right. Then we became detectives, looking for the signs. That big gap between training and validation performance. Validation scores getting worse over time and models that are just way too complex for the data available.
We unmasked the why, high variance algorithms being more prone, and the core issue of learning random noise as if it were signal.
And finally, the victory. Our optimization corner covered a whole arsenal of techniques regularization, L1, L2, early stopping, pruning, dropout, data augmentation, basic and advanced like mix-up, cut mix, batch norm, weight decay, all designed to control complexity and reduce variance.
Plus our listener challenge. Why 100% training accuracy can be bad news.
So the big insight, the aha moment really is, don't be fooled by perfect training scores. Evaluation on unseen data is absolutely critical.
Yeah, that performance gap is often more telling than the training score itself.
And this really matters, doesn't it, as we rely more and more on models for decisions?
We have to be sure
Yeah.
they're learning real patterns, not just echoes of the specific data they happen to see during training. It's about building trustworthy AI.
Absolutely. Which leads to a final thought, maybe something for you to chew on. In this data-driven world, how do we actively ensure our models are capturing genuine signals? What processes or safeguards can we put in place beyond just validation sets? Are there ethical considerations if an overfit model makes biased decisions based on noisy training data?
Hmm, that's a heavy one. Lots to think about there. Okay, on a lighter note, to wrap things up, why did the overfit machine learning model break up with the validation set?
I don't know why.
Because it said, you just don't understand me like the training data does.
Ah, nice. A fitting end. And seriously, if you want to explore these concepts further, do check out the resources we based this on. There's always more depth to uncover.
Definitely. Until our next deep dive.